Questions 8 through 10 on the 2007 Grade 12 Euclid Math Contest. In a 4x4 grid shown, 3 coins are randomly placed in different squares. Determine the probability that no 2 coins lie in the same row or column. Here's a 4x4 grid, and the best way to approach this problem is to label each of these squares from 1 to 16. Like that. And as always with probability questions, the very first thing I like to do is figure out the denominator. So the probability of something is always a fraction, right? It's something over something. 1/2, 1/3, 7 over 20, whatever. So first thing I like to do is figure out the denominator. And the denominator is the total number of cases. So first let's talk about that. The total number of ways of placing 3 coins into this grid. Well, how do we do that? First, let's look at the fact that we've got a first choice to make. And then, of course, we have a second choice to make, and then some third choice, right? So basically, in terms of choose notation, make it simple for us, it's from 16 possible slots, we have to choose 3. And that's all it is. That's all the denominator is. 16 choose 3. And 16 choose 3, if you remember, which I'm sure you do, is 16 factorial over 13 factorial, 16 minus 3, over 3 factorial. And in terms of numbers, this is 560. So there you go. You just got the denominator. Now we have to figure out the numerator. And the numerator in the probability questions involves the specific condition that the question is asking about. And in our case, the condition is that no 2 coins lie in the same row or column. So here we go. Let's talk about that condition now. We've got 3 coins to place. So let's take this one step at a time. Let's first say that the very first coin is placed right here in the one slot. So that's it. That's fixed. Now I have to figure out, where do I put my second coin? Well, remember, the second coin cannot be in the same column or row. So all of these are gone and all of these are gone. Those cannot be possible choices, because if they did, they would be in the same column or row. So I can only choose from these guys, and there's 9 of those. So I've got 9 possible choices for the second coin. Now the second coin, let's just choose one at random here. Let's say it's 12. If it is 12, I cannot choose 8 or 16, and I cannot choose 10 or 11. Why? Because those are in the same column or row. So the only choices I have left for my third coin are 6, 7, 14, 15. And how many of them are there? 4. So there we go. 1 times 9 times 4, which is 36. That is the number of possible combinations when the first coin is 1, right here. But what about if the first coin was, say, 2? Well, it would be the exact same thing in terms of numbers. It would be the first one, which is fixed. There's only one possible choice for the first one. In this example, for example, I've chosen 2. And then for the next coin, I can choose 9. And then for the third coin, I can choose 4. And you can do this, in your spare time, fiddle around with this, and you'll get 36. So in a very similar way, for each of these 16, you'll get 36. So 16 times 36, which is 576. So the numerator becomes 576. Yes or no? Well, immediately you should know, oh, there's something wrong here. Why? Because probability has always got to be less than or equal to 1. 576 over 560 is greater than 1. So that's obviously not correct. Why is it not correct? Because this 576 overcounts. And overcounting is a very big issue on math contests. Why does it overcount? Because each scenario is counted 6 times. For example, let's say my very first scenario was the first coin goes in 1, second coin went in 12, and the third coin, let's just choose 7, right? So my coins were 1, 12, and then 7. But there's 6 scenarios that are exactly the same, and those are 1, 7, 12, 12, 1, 7, 12, 7, 1, 7, 1, 12, and 7, 12, 1. See, the order can vary, right? In my example, I initially chose 1, and then I chose 12, and then I chose 7. But I could have done it in another way. I could have first put the coin in slot 7, then put the next coin in slot 1, and then put the next coin in slot 12. But if I did, it's the same thing. So each of these is counted 6 times. So this number I've overcounted by a factor of 6. So I have to divide 576 by 6 to get the number of unique different combinations. And if I do that, 576 divided by 6 is 96. So that 576 should not go there. What should go there is 96. All right. The fact that this probability, when I put the 576 in there, was greater than 1 actually helps you, because it immediately makes you think, okay, something's wrong. If it was less than 1, then perhaps a few people would not recognize that there was this overcounting going on. All right, now the only thing we have to do is reduce this to lowest terms, and reducing 96 over 560 to lowest terms is 6 over 35. And that is the probability. In the diagram, the area of triangle ABC is 1. Trapezoid DEFG is constructed so that G is to the left of F. DE is parallel to BC, EF is parallel to AB, and DG is parallel to AC. Determine the maximum possible area of trapezoid DEFG. DEFG, if I were to figure out the area, is the triangle ABC, subtract from that triangle ADE, and subtract from that triangle BDG, and subtract from that triangle CEF. So I'll explain that. This is what I want, that trapezoid. To get that, I have to take the full area, which is ABC, and subtract from that first this triangle ADE, then this small triangle BDG, and then this small triangle CEF. If I can do that, I will get the area of the trapezoid DEFG. And then I have to maximize that area. So this is the setup of this question. So first, let's use what we are given in terms of our heights and bases. Now I'm going to have to label a few things that is not present in the question. First thing, I'll draw a perpendicular from A down to the bottom, and then I'll draw another perpendicular from D down to the bottom like that. And each of these will represent the height. So this will be my small h, and this will be my big H, like that. So here we go. ABC, the area is 1/2 base, which is BC all the way across, times height, which I have denoted as the big H. ADE, in terms of the area, is 1/2 base, which is DE, times the height, which will be H, big H minus small h, like that, because we only want this distance right there. And then next we have BDG, which again is 1/2 base. BDG, the base will be BG, times little h, minus 1/2 base times height for triangle CEF. And that base, of course, is FC. And then the height is little h. So there you go. This is my equation. Now let's see if I can simplify this. And initially I just put that all over 2. And at this point, there's not much I can do to move forward, so I have to do a few other things before I can come back and work with this more. So the first thing I'd like to do is take advantage of this piece of information, which is the area of triangle ABC is 1. That's going to help me. So on the side, I will write triangle ABC. The area is 1. Well, 1/2 base times height. Base of ABC is BC, and the height is big H. And they tell me that area is 1. So if I were to simplify this, the most that I can do is just bring the 2 over and make this 2 is equal to BC times H. That's about as far as I can go with that information. And that helps me a little bit because BC times H is right here. So instead of putting BC times H, I can just put number 2, and the rest will be all the same. Okay, so at this point, where do we go from here? Now we have to use something called similar triangles. If you go back to the question, you'll notice they talk about parallel a lot. DE is parallel to BC, EF is parallel to AB, DG is parallel to AC. Why do they keep mentioning that? Because they're screaming at you to use similar triangles. When things are all parallel, they're basically spelling it out for you that, look, this is all similar triangles. That's basically what they mean by that. So let's use similar triangles. The first similar triangle relationship, I'll do it up here to be close to the diagram, is triangle ADE is similar to triangle ABC. So ADE is this guy, and ABC, of course, is the full triangle. And from that, you get the following relationship, that DE over H minus H, BC over H. And you can clearly see that DE over this height, which is big H minus small h, is equal to the big base over the big height. And that's the similar triangles notation, I guess. So any combination of this will work. For example, you can rearrange this as DE over BC is equal to H minus H over H, and so on. The next similar triangle relationship is between the big guy, ABC, and BDG, the small one, BDG. And if you do that, you get BC over H is equal to BG over small h. And again, any variation of this is also valid, like BC over BG is equal to big H over small h. And then third similar triangle relationship is between the big triangle and CEF. So this one right here. So in a very similar way, you can get a relationship between the sides. BC over H is equal to FC over small h. And I can rearrange this as needed. For example, BC over FC is equal to big H over small h. So this information that I just calculated is what we are going to place in this. Why? Because eventually we want as few variables as possible, because we have to maximize this equation. And currently, there's no way I would know how to maximize this because there's way too many variables. But if I can bring it down to one variable or two variables that have a relationship, then I will be able to maximize that. So here we go. First, let's just fill this in, and then I'll scroll up. So we've got 2 minus DE, but DE, I'm going to use this to get rid of the DE. And I think since there's a BC everywhere, eventually I think everything should be in terms of BC. And that probably is the best approach, because that seems to be common everywhere. All right, let's put DE in terms of BC. So that's going to be BC times H minus H. Instead of saying big H and small h, I'll just say H minus H. I mean, you understand. And I think that's it for DE. And then, of course, just make sure you do this algebra very carefully, I've got an h minus h here. Okay, BG here. BG, this BG I can get from this guy, and that's going to be in terms of BC, and it will be BC times small h over big H, like that. And then don't forget this h, the small h. And then finally FC, I will get a relationship from this one, and that's going to be BC times, again, small h over big H. And don't forget that small h right there. There we go. And oh, also don't forget this is all over 2. Okay, so here we go. Now we can work with this. It's a little bit tricky, but if you don't make any mistakes, it should be okay. So let's try and collect as many like terms as possible. And what I see at this point is that there seems to be a BC everywhere. So I can factor out that BC, and then I'll have a whole bunch of stuff in the brackets. Like that. And let's do one final simplification here. I believe that this 2 and that 2 can cancel, and then we can add these two guys together. Now at this point we have to start discussing this. Remember, this whole thing was equal to DEFG, right? That is the trapezoid that we have to maximize in terms of its area. And it equals this whole thing. So let's discuss this now. We want to maximize this. 1 minus this whole thing. This whole thing will be maximized when what you are subtracting is minimized. What are you subtracting from 1? You're subtracting that. So again, I'll repeat it. This whole thing will be maximized when this is minimized. I hope that makes sense. If it does, let's move forward. So you are trying to minimize this. Well, BC is fixed, right? I'll write that in here. BC is fixed. That's not going to change. But what will change is the small h. That is really the only thing that changes. Even the big H is fixed. Big H is also fixed. So, our task is to minimize this guy right here. Now, how do we minimize this right here? That is the question. We've got 2 variables. If there was only 1 variable, probably would be a little bit easier to minimize something. But there's 2 variables. How do you minimize that? Well, the first thing is h is fixed. So h never changes in this question. It's just the height of the big triangle, ABC. So we can get rid of that. We don't need to worry about that. It's like having 5 down here. So we can now concentrate on just the top. Let's minimize this. H, big H minus small h squared plus 2 small h squared. Let's minimize that. So there's a couple approaches. The first approach is by plugging away numbers, like what can h possibly be in terms of the small h, but that's going to take forever and it's not scientific. The absolute way of doing this is by making a relationship between the small h and the big H. Now, if you recall in the diagram, the small h is right here, the distance from there to there, and the big H is top to bottom. Now, the small h and the big H are related in some way. The small h is some fraction of the big H, and that is what we are going to use to ensure that this becomes one variable. So h is some fraction of big H, right? Because we know that small h is less than h. So I can say h is equal to m times big H, where m is between 1 and 0, correct? So for example, h is, I don't even know, 7 over 10 big H. It's some fraction. And in this case, my m is 7 over 10. That's essentially what this notation is. Don't get confused. It's not trying to be tricky here. I just want to get everything in terms of one variable. So what I'm going to do is instead of putting in all of these variables like that, I'll substitute small h is equal to m big H, and that allows me to get everything in terms of one variable and factor out something, and you'll see what I mean. Currently I can't do that here. I really wanted to try, but I quickly realized that that would not be possible. So here we go. We've got big H, and instead of small h, I'm going to put mh, and this is all squared, plus 2 times mh all squared like this. So this becomes h can factor 1 minus m all squared plus 2m squared h squared. This, when you expand it, becomes h squared, and then in the brackets it'll be an expansion of the form 1 minus 2m plus m squared plus 2m squared plus or times h squared like this. So far so good. And now we can factor out the h squared from everything, and we'll get something in terms of just m, and that is going to be, if you add like terms, 3m squared minus 2m plus 1. And this, what I just did, in my opinion, is the heart of the question. This allows you to minimize this. Remember, h is fixed, so if I can minimize this, I'm done. Notice that this is the equation of a parabola, and because the coefficient of m squared is positive, it's a parabola that points up like that. And this parabola has a minimum point right there, and that minimum point is the vertex. And the vertex of a parabola, if the parabola is in this form, will be hk. So our task is to get this into this form. If we do, we can get the minimum value of m, and that will allow us to figure out the minimum value of this whole expression right here. So how do we get this into this form? You do that by completing the square. The first thing, of course, is we have to factor out the 3, and we do that. That gives me 2 over 3m, and then I'll just put this 1 out here. Now to complete the square, the process is you have to first take half of this number and then square it. So half of 2 over 3, negative 2 over 3, is negative 2 over 6. So then I have to square that. That would become 4 over 36. And then, of course, I have to subtract the same thing immediately. I can't just add something and without subtracting it. And there you go. That's basically the process of completing the square. Now, of course, I can factor it to make it look like this. And if I do, it will become, in this particular scenario, m minus 2 over 6 all squared. And then be careful, this factoring involves those 3 terms. So I have to take this and multiply it by this and kick it out of the brackets. If I do, I get minus 12 over 36, and then this lone 1 out here. So just don't make any algebraic mistakes there. This basically becomes 3 times m minus 1/3 all squared, and then this is going to be plus 2/3. So there we go. The minimum value occurs at the vertex, and in this case, what is my vertex? It is 1/3, 2/3. The minimum value occurs when m is equal to 1/3. There we go. We're almost done. Now, what is m? What was the significance of m? If you recall, m is giving me the fraction of the big H that equals small h. So that basically means that since m is 1/3, that small h is equal to 1/3 of big H. That is going to give me my first and foremost, minimum value of all this. And when I plug that into our original equation, which is right here, it will give me the maximum value of that, correct? As we had discussed before, to get the maximum value of this, I have to get the minimum value of this. And that's what we've done. So now we have to take our equation that is right here and substitute our finding that h is equal to 1/3 of big H. So let's take this equation and substitute this finding, and that will allow me to get the maximum value of DEFG. So in my equation, I'm going to substitute for small h, I'm going to put our finding, which is 1/3 big H. So it becomes h minus 1/3 big H, like that. And then that is all squared. And then over here, I've got 2 times small h, which is the 1/3 big H, all squared, all over big H. There we go. So this becomes 1 minus BC over 2. And then now I've got some algebra to do. Well, first and foremost, h minus 1/3 h is 2/3 h. And then that's all squared, all over h. Plus, this is going to be h squared over 9. And that's times 2. So that's 2h squared over 9, all over h. So it simplifies pretty quickly here. And then this looks like 4h squared over 9, invert and multiply 1 over h, plus 2h squared over 9, invert and multiply 1 over h, like that. So again, I've got 1 minus bc over 2. In the brackets, that looks like the h's will cancel at least one of them, so you're just left with 4h over 9 plus 2h over 9. And then this looks like 1 minus bc over 2, 6h over 9, like that. And if you put everything together, this becomes 1 over 3 over 9, which is 1/3, times BC times H. Now BC times H, if you recall, was equal to something right here. BC times H was equal to 2. So, very helpful. We can plug that in. So that's equals 1 minus 1/3 times 2. And that becomes 1 minus 2/3, and that is equal to 1/3. And there we go. After all that, we got the value for the trapezoid DEFG. That is the maximum possible. So we have answered the original question, which is determine the maximum possible area of trapezoid DEFG. The parabola y is equal to f at x is equal to x squared plus bx plus c has vertex p, and the parabola y is equal to g at x, which equals negative x squared plus dx plus e, has a vertex q, where p and q are distinct points. The two parabolas also intersect at p and q. A, prove that 2 times e minus c is equal to bd. This is a rough diagram that illustrates this question. This parabola is f at x. And the reason that I know that it points upwards is because the coefficient of x squared is 1, which is positive. And this parabola that's pointing downward is g at x. And the reason that I know it points downward is because the coefficient of x squared there is -1, negative. And they tell me some interesting things. The first is that the vertex for the first one is p. So that's the vertex right there, label that P. And the vertex of the second one is equal to Q in terms of their notation. And they also tell me that the two parabolas intersect at those very same points, P and Q. So that's just a rough sketch, just to kind of illustrate what's going on here. Now our task is to prove this right here, 2 times E minus C is equal to BD. Now at first you might think, well, I don't even know where to begin here. But don't get discouraged. Just use the information that they've given you in the question. That is sufficient. You don't have to pull something out of, left field. Just information in the question and the diagram. And those pieces of information are as follows. The first thing, of course, is to figure out these intersection points. Now, they're going to be in terms of letters, but that's fine. And then, once you do that, we can compare them. And when you compare them, we will somehow, some way arrive at this. So here we go. The first thing is we've got our two equations. F at x is equal to x squared plus bx plus c, and g at x is equal to negative x squared plus dx plus e. Those are the two equations given in the question. Now we know for a fact that they intersect. They intersect here and they intersect there. So we set them equal to each other. So that means x squared plus bx plus c is equal to minus x squared plus dx plus e. Right? Straightforward. Put everything on one side, collect like terms. You get 2x squared plus b minus d x plus c minus e is equal to 0. This is a quadratic, correct? And like any quadratic, use the quadratic formula. X is equal to minus b, like that, plus or minus the square root of b squared minus 4ac. All over 2a. All right, that's it. That's the first part. The second part is going to figure out the formula of the parabola, but in a slightly different format. Which format? Well, this format right here. Ax minus h squared plus k. Why? Because in this format, we can immediately tell what the vertex is. It's hk. And our vertex, for example, for the first one is P, and for the second one is Q. Now, what I've already figured out by doing this is this X and this X, right? Those are the 2 points of intersection. My assumption, which should be correct, is that the minus part of this guy right here, refers to the P, and the plus part refers to the Q. Right? Because P seems to be less than Q in terms of the x-axis. All right, let's get this into this format. And how do you do that? Well, you do that by completing the square. And I'm sure you're familiar with the completion of the square. X squared plus bx plus c, complete the square. How do you do that? You take half of this coefficient and you square it. So we got x squared plus bx. Half of that is b over 2, square it, so b squared over 4, and then subtract b squared over 4 plus c. Now we can square, so bx plus b over 2, all squared. And then, of course, that involves those three, so we have to now treat these two independently. So I'll just put it out like this. And there you go, we've got it into this format. And therefore, the vertex P is minus b over 2, and then c minus b squared over 4. This is the x coordinate, this is the y coordinate. And now we make a comparison. We've got the x coordinate here, we've got the x coordinate here, we set them equal to each other. And my hunch is that is going to allow me to figure out that proof. So as I previously stated, I strongly believe the negative part is the one that corresponds with P, since it seems to be smaller on the x-axis. So we set that equal to each other. We've got d minus b minus the square root of b minus d squared minus 8 times c minus e. And that is all over 4. And that is equal to this guy right here, minus b over 2. And this should be sufficient, I hope. Let's see. Let's see what we can do immediately. Let's get rid of the fractions here. Let's multiply through by 4. And if I do, I'll get the following. And now I'd like to put everything on one side that has a radical and everything on one side that does not have a radical. And if I do that, I get d plus b on this side, and then I get the big long radical on the other side like this. And then of course at this point I've got to square both sides to get rid of that square root. And if I do, on one side it will be d squared plus 2bd plus b squared, and on this side I just get what's underneath the square root sign, which is b minus d squared minus 8 times c minus e. All right, now at this point shouldn't be too bad. So let's see here, let's expand this. D squared plus 2bd, this stuff doesn't change, but then this, we got b squared minus 2bd plus d squared, and I'm just going to keep that part the same because that I can change that into a plus 8 and then reverse this because it's starting to look very similar to this. All right, now let's see what we can do. The d squareds cancel, the b squareds cancel, put this on the other side, and I get 4bd is equal to 8e minus c, and there we go. Divide through by 4, and you get bd is equal to 2 times e minus c. And that is exactly what they wanted us to prove. So there you go. I really hope that this is question number 9 on the Euclid. And I really hope that you were able to follow this and develop the self-confidence that when you read a question, don't just immediately say, oh, I can't do it. That's beyond me. I don't know how to do it. Work with the question. See, I didn't do anything that was crazy. I didn't do anything that was outrageously difficult. All I did was draw a diagram and just work with what information they gave me in the question. Part B, prove that the line PQ has a slope of 1/2 b plus d and a y-intercept of 1/2 c plus e. Let's go back to the diagram. Line PQ, that would be a line connecting P through Q. So basically a line like this. This line is what I have to work with. I have to first figure out the slope, the intercepts, and hopefully with the information I've obtained so far, this shouldn't be too much of a problem. So here we go. Therefore, I've got to prove for this line PQ that is always going to be of that form, y is equal to mx plus b, that the slope m is equal to 1/2 b plus d, and this y-intercept, which I've called large B, is equal to 1/2 c plus e. These are the things I have to prove. So the first thing I'm going to need is the coordinates for P and Q. Now the coordinates for P, I think I already figured out previously right here. So let's write that in. And the coordinates for Q, we can figure out in an identical way by completing the square for the equation of g at x. So what was the equation for g at x? If you recall, it was minus x squared plus dx plus e. And first let's factor out the minus 1. That gives me x squared minus dx plus e. And now complete the square. Remember, you take half of this coefficient and square it. So it would be d over 2 is half. So half of it, if you square it, becomes d squared over 4. And then immediately I have to subtract that, like this. And then this allows me to complete the square with those three terms. It becomes x minus d over 2 squared. and then kick this guy out, but don't forget to multiply by that coefficient, and we get d squared over 4 plus e. So this allows me to figure out the coordinates for q, which are in this case d over 2 and e plus d squared over 4. So now I can figure out my slope, which is m. And remember, slope is always rise over run, correct? So using these 2 points, I can do that. Rise would be the difference from p to q, but with regard to the y coordinates. So that's going to be e plus d squared over 4 minus c plus b squared over 4, correct? And the run is the difference between the x coordinates. So that's going to be d over 2 minus b over 2. So it becomes plus b over 2. All right, so here we go. Now we've got to do some algebra here. All right, so let's see. We can use the fact that we just proved something. Immediately I look at E and C, and it reminds me of part A. If you remember, not too long ago, we proved that BD is equal to 2 times E minus C, correct? So therefore, E minus C is BD over 2. So we've got E minus C here. So instead of having E's and C's, let's just put in BD over 2, since we know that as a fact. So we got BD over 2 plus D squared over 4 plus B squared over 4. And on the bottom, we've got B plus D over 2, like that. And on the top, you'll notice that if I multiply top and bottom by 2 and then collect like terms, we got B squared plus 2BD plus D squared all over 4. And then I'm going to invert and multiply this, so 2 over B plus D, like that. And then this factors very nicely. It becomes B plus D all squared all over B plus D. And we've got a 1/2 sticking out here. And then finally, the B plus D's cancel, so all I'm left with is just B plus D over 2. And that proves the first part, that the slope is equal to B plus D over 2. There we go, that's exactly what we got. Now we have to prove that the y-intercept is equal to C plus E over 2. So let's do that. So remember or recall that the equation of the line was y is equal to mx plus b, large B. I just didn't want to confuse with the small b. And we just calculated that the slope is equal to b plus d over 2. So we substitute that in. Now the y-intercept we get when we set x equal to 0, correct? Or we can substitute any value or any point that's on this line. Well, we know 2 points rather. The first point we know is P and the second point we know is Q. So we can substitute either of those into this equation to solve for B. Now, either one is fine. I'll just use P. P we had figured out earlier was equal to minus B over 2, C minus B squared over 4. So I'll substitute P into this equation. So the y coordinate is C minus B squared over 4. And then my slope is B plus D over 2. My x coordinate is minus B over 2. And then I've got this big B. So that's why I use the big B, because we've got small b's in there, and I didn't want to get that confused. All right, so we got some algebra to do. The first thing, of course, as always, try to get this all into one fraction. So I'll multiply top and bottom here by 4. And this basically will become 4c minus b squared all over 4. And this becomes minus b squared minus bd all over 4 plus b. And put everything on one side. And if I do that, I get 4c minus b squared plus b squared plus bd all over 4, like that. all equal to b. Now, recall earlier we proved in part A that BD was equal to 2 times E minus C. So we're going to put that in. Notice these two cancel, which is very good. And all that's left with is 4C plus BD. But BD we had proved earlier is equal to 2 times E minus C, like that, all over 4. So we've got 4C plus 2E minus 2C all over 4. And we're almost done here. Let's see, we've got 2C plus 2E all over 4 is equal to B. And therefore B is equal to C plus E over 2. There you go. We just got that the y-intercept is equal to C plus E over 2, and that's exactly what they wanted us to prove for 9b. Number 10, in the diagram, the circle is tangent to xy at y and to xz at z. Point T is chosen on the minor arc yz, and a tangent to the circle is drawn at T, cutting xy at V and xz at W. Prove that the perimeter of triangle VXW is independent of the position of T. A few lines we will draw in. The first is from the center of the circle to Y. The next is from the center to Z, and these are all tangent points. And the next is from the center to T. And those are all tangent points, so they create all right angles. And this is a circle, right? So basically, this is going to be R radius, that's the radius, and that's the radius, like that. Okay? So we can use Pythagoras since we've got so many right triangles. The first one, of course, is right here. This triangle that I create, and then I'll do the same thing with this triangle that I'm going to draw to V, and I'll explain. In this triangle right here, we get that Vy squared using Pythagoras plus R squared is equal to this right here. But that is also equal to Vt squared plus R squared, correct? Since they have the same hypotenuse, those two triangles. So Vt squared plus R squared. And therefore from this equation, the R squareds cancel. That means Vy squared is equal to Vt squared. And if you take the square root of both sides, Vy is equal to Vt. Vy is equal to Vt. That's the first finding. Then we'll do pretty much the exact same thing, but with these two triangles. From the first one, we get that R squared plus Tw squared is equal to R squared plus Wz, correct? Because both of them share the same hypotenuse. R squares cancel, so that just leaves me with Tw is equal to Wz all squared. And if you take the square root, you get Tw is equal to Wz. So that's the first thing. Now, what is the perimeter of triangle VXW? The perimeter of triangle VXW is XV plus VW plus XW, right? Now, XV is what? XV is basically from here to here. But we can write it in terms of XY minus VY, correct? So all this should make sense very soon. Instead of writing XV, I'll write XY minus VY. Similarly, VW is right here. Now VW, instead of writing VW, I'm going to write VT plus TW because it's equivalent. So we got VT plus TW. And finally, XW, instead of writing that, I'll write XZ minus WZ. like that. Okay, so here we go. Now we have to match all this together. So we got xy minus vy, but vy is the same as vt. That was what that whole deal was about. So I write vt. Then this is vt plus tw, correct? Plus xz minus wz, but wz is the same as tw. So put that in there. Now I hope you can see that a lot has canceled. These two are gone, and this tw cancels with this. So the only thing you're left with for the perimeter is xy plus xz, right? That's the only thing that's left. And xy plus xz, if you go back to the diagram, here's xy and here's xz. They are completely independent of where t is. T could be anywhere. T could be here, it could be here, it could be here. It doesn't matter. Where t is irrelevant to the values of xy and xz. xy plus xz is a constant. It's always the same, regardless of where t is. So that completes our proof that the perimeter of triangle VXW is always a constant, independent of the position of t. In the diagram, AB is equal to 10, BC is equal to 14, and AC is equal to 16. And M is the midpoint of BC. Various lines can be drawn through M, cutting AB, possibly extended at P, and AC possibly extended at Q. Determine with proof the minimum possible perimeter of triangle APQ. What I would like to do is use the previous question. Usually part B, it follows part A in the way that what we found out in part A will help us. So what did we find out in part A? Well, we just did it a few minutes ago. We found out that the perimeter of this particular triangle, which is XVW, is summarized as follows. It is equal to XY plus XZ, independent of where T is. Correct? We just did that. So now we've given this situation here, where it seems like it's exactly the same in the sense that instead of XVW, we've got ABC, like that. But the only difference is now they've thrown in this PQ. So to keep things as simple as possible, what I'll do is I'll try to superimpose this onto here. And it shouldn't be that difficult to understand. This X, they have just called A. So I'll just write A or X. This W, they are calling C. So I'll just write C or W. Same letters in terms of the points. And this V, they're calling B. So I'll just write B dash V. Okay, that's all the same. Now, the new thing that they've introduced is this line PQ. So, this PQ is something like this. We don't know exactly. It could be something like that. It could be something like this. We're not sure. We don't really know at this point where exactly PQ lies. But if you analyze this diagram, you can conclude that the perimeter of this triangle, whichever letters you want to use, whether it's XVW or whether it's ABC, that perimeter will be minimized when PQ is tangent to the circle, exactly the way VW is. Because if you notice, if you were to draw PQ in any other way, if you're drawing it like this, or if you're drawing it in any way, it will make the perimeter greater. But the perimeter will be minimized when PQ is tangent to the circle, exactly the way VW is. So in summary, analyzing the diagram, you can conclude that the perimeter of triangle APQ is minimized when PQ is tangent to the circle. And basically what that means is that PQ is equal to VW. That is the scenario that will minimize the perimeter of triangle APQ right here. So don't want to make this too confusing, but instead of VW, we are placing there PQ, this PQ right here. We're putting PQ in the same spot, like that. So I'll put P right here and Q right there. I know we got too many variables all representing the same thing, but I just wanted to keep it all in one diagram to make it easier to understand, and I hope this is easier, not easy, but easier to understand. Okay, so here we go. We established that first point. Now, we also know that the minimum perimeter of that triangle, whatever you want to call it, you want to call it APQ, or you want to call it XVW, the minimum is going to be that, XY plus XZ. We established that in part A. So therefore, the minimum perimeter of triangle APQ is AY plus AZ, right? This is triangle APQ, and the minimum perimeter is A to Y and A to Z. And that occurs when PQ is equal to VW. All right? So here we go. The first thing I want you to understand or notice is that if you draw a line from A to Y, and Y is tangent, and then you draw another line from the same point A to Z, and Z is also tangent, that means that these two lines are equal in length, AY and AZ. In summary, since AY and AZ are two tangents drawn to the circle from the same point, AY is equal to AZ. So that means I can substitute that back into this perimeter formula, and if I do, I get that P is equal to 2 times AZ, right? Because AY is equal to AZ. So that is a very important finding right off the bat. P is equal to 2 times AZ, where AZ is from here to here. Now in the question, they had given us some very important lengths. If you recall, they told us that the distance from A to B was 10, and the distance from A to C was 16, and the distance from B to C, right here, was 14. So that's very helpful because that can allow us to figure out some angles. And the angle that I want to figure out the most is this one right here. So how do I do that? Well, by using the law of cosines. 14 squared is equal to 10 squared plus 16 squared minus 2 times 10 times 16, the cos of A, this angle right here. And that gives me, if I bring everything over, 320 cos of A is equal to 100 plus 256 minus 196. And this is 160 all over 320 is the cos of A. And therefore A, in terms of the angle, will be 60 degrees. All right, so that's the very important point in this solution. So to avoid making this diagram too messy, I just wanted to duplicate it. Now, I would like you to look at this diagram in a slightly different way. First, I'm going to draw a line from the center to Z, and then I'm going to draw a line from the center to Y. I had done this previously, so I'll do it again. And now I'm going to draw a line from X all the way to that center. Okay, like that. Now, a few things I have to carefully point out here. This line that I drew from the center to Z makes a 90-degree angle, correct? Because XZ was tangent to the circle, so that's 90 degrees. This full angle we just figured out was 60 degrees. Now, when you draw a line from X to the center of the circle, it cuts that angle in half exactly. So that means this angle is 30 degrees, and therefore this angle is 60 degrees. So once again, we have a 30, 60, 90 triangle. And the ratio of the sides of a 30, 60, 90 triangle are 1, 2, and root 3. So we know that this is the radius r. So therefore r over this whole distance right here, which is xz, is equal to 1 over root 3. And therefore xz is equal to root 3r. Okay? Now remember, we had used slightly different letters to represent the exact same thing. And I'm not sure why they did that in the question. Why did they change the letters on everybody? Why did they just use the same letters for both part A and part B? But it's okay. It's not that big of a deal. We'll just put A there. That really just means that AZ is equal to root 3r. And what I can do is I can put that into this formula, and we get a very nice result that the perimeter is equal to 2 times AZ, but AZ is root 3r, so 2 times root 3r. So this is going to be our perimeter. Now all we have to do is figure out r, which is the radius of that circle, and we'll be done with the question. So to figure out r, we have to turn our attention to this circle. And this circle is going to be at the heart of our solution from now until the end of the solution. How so? Well, the first thing we have to do is figure out the equation of this circle. Now, the equation of any circle is of the form x minus h squared plus y minus k squared is equal to r squared. And h and k represent the center. Is equal to the center of the circle. Now the center of our circle is right here, correct? But what are the coordinates there? Well, if we were to place this on a coordinate plane, it would make a little bit more sense for us. So let's do that. This line will just represent my x-axis. Okay? That's my x-axis. And this line right here will represent my y-axis. Okay? There we go. Well, the distance from here to here represents the x-coordinate of the center. And the distance from here to here represents the y-coordinate of the center. So my center for my particular circle here is root 3r, r. And whatever you want to use, you can use big R, small r, it doesn't matter. I'll just use big R. So that means my equation is x minus root 3r all squared plus y minus r all squared is equal to r squared. Okay? Now, to figure out r, I have to first substitute some value for x and y. I have to substitute a point on the circle into this equation. If I can do that, I'm set. I can figure out the value for r, then I can put it into this perimeter formula, and I can calculate the perimeter. So my final step is to figure out at least one point on this circle. So which point am I going to use? Well, we have to go all the way back to the beginning of the question where they tell us that there's going to be a midpoint here. So here's that original question. You'll see M is the midpoint of BC. So BC was here, and there was a midpoint. And that midpoint is very important because that midpoint represents, in our diagram, the exact point that touches the circle. It is the tangent point. So what they did was they gave us this diagram initially with BC like this, and they said that M is the midpoint of BC. When we introduced the circle into the diagram, we concluded that our line that we are going to use has to basically be tangent to the circle. So if it's tangent to the circle, this M point is the point that is tangent to the circle. That is the exact point. So that point M is on the circle. So what I need to do is figure out the coordinates of M, and if I do, I can substitute it back into the equation of the circle. Why? Because M is on the circle. It's the tangent point. And how do I figure out M? Well, M is the midpoint of BC. So if I can figure out the coordinates of B and C, then I can figure out M through the midpoint formula. So here we go. Let's figure out the coordinates of B and C. Remember, they gave us in the question that AB is 10, and they also told us in the question that BC is 14, and that AC is 16. And we just figured out earlier that this angle was 60 degrees. So if we want to figure out, say, B, and remember we had placed this on a coordinate plane like this, where this is the x-axis and this is the y-axis, like this. If we can figure out the coordinates of B and C, then we can figure out the coordinates of M. So how do we do that? B, the coordinates, will be as follows. Cos of 60 is equal to this, which I will denote x, over 10. And therefore x is equal to 10 cos 60. And therefore x is equal to 5. Now what's the significance of that? Well, that is the coordinate for B, at least the x coordinate. Okay? And then to figure out the y coordinate for B, which I will just denote y, you would use sine. So the sine of 60 is equal to y over 10, and therefore y is equal to 10 sine 60, and therefore y is equal to 5 root 3. So there we go. We just got the coordinates for B. Now the coordinates for C is a little bit simpler. It's just right on the x-axis, right? So its x-coordinate is essentially just the distance from A to C. And that's just going to be 16 because this is equal to 16. And the y-coordinate, of course, is 0. So there we go. Now we can figure out the coordinates of M using the midpoint formula. M will be, remember you add this and then divide by 2. So it's 5 plus 16 divided by 2, and then similarly 5 root 3 plus 0 divided by 2. And this gives me 21 over 2 and 5 root 3 over 2. And now all I have to do is substitute this point back into my equation of the circle. So that's my final step in this question. So I got 21 over 2 minus root 3 r all squared plus 5 root 3 over 2 minus r all squared is equal to r squared. So expanding, we get 441 over 4 minus 21 root 3r plus 3r squared plus 75 over 4 minus 5 root 3r plus r squared is equal to r squared. Simplify and put everything on one side, and we get 3r squared minus 26 root 3r plus 129 is equal to 0. Now, of course, we have to use a quadratic, so r is equal to minus 26 root 3 plus or minus the square root of minus 26 root 3 squared minus 4 times 3 times 129 all over 2 times 3. Simplifying, we get r is equal to 26 root 3 plus or minus 2028 minus 1548 all over 6. And therefore r is equal to 26 root 3 plus or minus the square root of 480 all over 6. And this is going to be 26 root 3 plus or minus 4 root 30 all over 6. And if you simplify this as much as you can, you will get 13 root 3 plus or minus 2 root 30 all over 3. So we get two values for r, and in terms of decimals, if you were to figure it out, it's about 3.8, and the other one is approximately 11.1. And between those two, the one that makes sense, that fits the dimensions of our diagrams, is this one right here. So r, therefore, we conclude is 13 root 3 plus 2 root 30 all over 6, all over 3 rather, like that. So we're pretty much done. We have to now just figure out the perimeter, and remember the perimeter right here, we had figured out a very nice formula, 2 root 3 r. So we have to figure out the perimeter using this formula and this value for r. Substitute that in, and we get p is equal to 2 root 3 times 13 root 3 plus 2 root 30 all over 3. And when you multiply that, you get 26 times 3 plus 4 times root 90 all over 3. And this looks like 26 plus 4 root 10 when you simplify. So there you go. That is the perimeter. That is the minimum possible perimeter for triangle APQ.